All right, let's get started. Test number 1. Let's do it. I will say just general impressions is some of you folks don't remember my little tips. I've tried to give you tips and I could say, don't do this. And inevitably people will do this. And I said, don't do this. Highlight this in your notes, redline it. And this will prevent you from having some progeny when you do the test. And in a lot of cases, I saw people doing exactly that. So let's get started. We'll see if you can pick up on some of these. So I have a load that's being fed from a transmission line. The line can be represented like this, 50 plus J100. Here's the load. The load is 15 MVA. And the power factor is 0.85 lag. The line is 115 kV, so we'll assume that the voltage is also going to be operating at that kV. So the first question is the line current of the load. Question? Oh, you walk in late? You're Luke, right?
Yeah, Ryan.
Oh, sorry. Come on down. Ryan Bernard?
Yep.
What's that?
Yep.
Okay. So the idea is we have 115. Where does the 115 kV live? Across the load. A lot of you said, I'm dropping 115 kV here. Is that true? Why would that not be true?
That's 0 volts on the load.
Yeah, if you put 115 kV drop over here, how much power are you delivering to your customers? None. So your transmission line is a nominal rating of 115 kV. There's no way you should be dropping anywhere near close to that voltage. If you are, why run the transmission system? Because you're not going to be able to sell any power. So you have to put the 115 kV at the load. And don't forget, we want everything to be single phase to do our calculations. Convert that to single phase. Make sure that is converted to an equivalent voltage. And then set that equal to 0. So my current, my line current, because that's the same current going to my load, I is going to be equal to 5 MVA at a 0.85 lag divided by that. Yes, sir. For the voltage or for the power? Because for voltages, let's just draw it as a Y-connected one. This is a voltage. This is a voltage. Remember, it's plus to minus. When you add those vectorially together, you get something like this. And this voltage over here is the square root of 3V. So if you remember, one of the little tips I gave you is only use the square root of 3 for phasors. You never use square root of 3 for anything else. So that implication is only use the square root of 3 for phasors, never use 3 for phasors. So to do the conversions, you need to use a square root of 3 if you're talking about voltages and currents, which are the only 2 phasors we have. Question 8.
That one wasn't set up.
Didn't need to be.
Okay, so how do you know? If you just know that you need to do this square root of 3 just because of the previous system.
Remember this equation here? That's our general equation for getting 3-phase. If you recall, we also said it's square root of 3, V line, I line conjugate, right? In a Y-connected circuit, the line current is the same as the phase current. In a delta connected circuit, the line voltage is the same as the phase voltage, but they're not always the same. So you always have to divide square root of something by the square root of 3. Either I'm going to divide the current by the square root of 3 or the voltage. So by using this equation, and then just saying, let's just divide the voltage by the square root of 3, I've included the fact that whatever current that I'm going to calculate has already had that square root of 3 divided out. So it just massively simplifies, what it is by just putting it on the voltage. You could have had a delta, but then we'd have to go ahead and say, oh, well, the current over here is going to be the square root of 3 times the phase current. So you would have had to do it at that point anyway.
If you were to use that one square root of 3, B line, I line, wouldn't you not divide the S by 3?
Yes, so I wouldn't divide the S by 3, but keep in mind, I put in a voltage over here. That's not a line voltage. It's 115 kV divided by the square root of 3 is a phase voltage.
So you can do it.
Right. So I did both phase voltage and phase current. That's why I divided by 3. If I would have used this equation here, then I wouldn't have divided that voltage by the square root of 3. I would have put it in 115 kV. Okay. So when you do this calculation, my I (75.3) at an angle of minus 31.8. What does this current have? Two pieces of it, right? What are they? Magnitude and angle. In AC circuits, your currents and voltages should almost always have magnitude and angle. That was one of the other hints that I gave, that you always need to provide a magnitude and angle unless I'm telling you what is the magnitude of the current. If I'm asking for the current, you don't give me a magnitude, you give me magnitude and angle. So to get full credit on that, I needed to see 75.3 at an angle of minus 31.8. Then you can also check your work. It's a 0.85 lagging power factor. Does that give me hope that the power factor is correct? Well, the current lags the voltage. I said my voltage here is at an angle of 0. So the current is minus 31.8 degrees. The voltage is at 0. So minus 31.8. I feel pretty confident. Next part, line power loss. This is another one of those tips I gave you. Line power loss is P lost in the line. It's I squared R. Magnitude of I squared R. It is not equal to can't do that. You got to multiply by the magnitude of I. So it should have been I squared R. Or magnitude of I squared times R. A lot of people put Z's in there. A lot of people put complex numbers. And so your output was you got power that had complex. I was just looking for the load power. So be very careful, because the equation doesn't work if you just square the current. You get really wonky results. You have to use I magnitude squared R. And then the last question is, what is the power factor of the load? Power factor is equal to the cosine of the difference in angle between the current and the voltage, which is equal to the cosine of 31.8, which is equal to 0.85. And then, and the angle on I was negative. Did you ever see anything else about what, did you ever find 0.85 lagging anyplace else?
First.
What's that? In the first one?
Yeah.
How about in the description of the problem? It said, what is the power factor of the load? I gave you the power factor of the load. You just had to write down 0.85 lagging. You didn't have to do the calculation. You could have sanity checked your work and did this part. And then that's what my hope was, is for those of you who weren't feeling confident, you would have sanity checked, said, hey, what's the cosine of 31.8? Oh, it's 0.85. Well, it should be 0.85 because that's what the power factors of the load. That's the problem description. Question on number 1. No questions? Or are we still confused? Question?
It's just clarifying with the PL, if you had.
Oh, yes, sorry. This is for single phase. Forgot to multiply. I have 3 phases, so I have to multiply by all 3. It has to be single phase because this is a single phase resistor, right? So I run the current through the resistor, square that, multiply by R, and that is the, because I've got 3 resistors. I've got 3 transmission lines, so I have to have power, the total power loss is 3 times that value.
But you use I line and not I phase.
Absolutely. I use I line and not I phase. Why is that? Because this is the current running through the line. The line current and the phase currents are the same. Right? If you had assumed it was a delta, then you have to multiply by the square root of 3. But in this case, because we simplified it all down, we just calculated line currents, and that was a current going into the load. I don't really care how the load is connected. I'm good to go. I've got my answer. Questions on that? Should we move on to number 2 or? I was really hoping to see some pictures in this next problem. Why do you like to see pictures? Because it really tells me a whole bunch of information. I'm just going to call this ZY and Z delta. So those 2 loads are in parallel with each other, correct? Is ZY in parallel with Z delta? What's the rule for having loads in parallel with each other? What's unique about them? They had 2 nodes in common, right? This is node 1. This is node 2. Is that the same as node 1 over here and 2 over here? Not, doesn't look like it to me. What I could have done is instead of having, let me erase this a little bit. Instead of having this delta, I'm going to convert that to a Y. And then this is equivalent. Is node 1 and node 2 of the equivalent delta converted to Y the same? Node 1 and node 2. Oh, nope, they're not the same. Right? Node 1 and node 2 aren't the same. But they are. Because in a balanced system, this is at 0 volts. And this is at 0 volts. So even though there's no connection between them, they are electrically at the same potential. So it's the concept of an op amp where you have a virtual short. It's the same thing here. Remember we talked about neutrals and why I don't need to run them? Because the voltages on the neutral are the same potential. It's the same point. And when we did single phase equivalent analysis, we just converted our circuit like this. Right? That's with the line. In this case, these are electrically at the same point. I can connect them like that. So to do this problem, you had to convert one of them to a Y or delta. You get to pick. And then you put them in parallel. This one I was a little bit concerned because some people said Z of the delta is equal to 3 times Z of the delta, or Z of the Y is equal to 3 times Z of the Y. No way. They are not in series with each other. In series would imply that you only have this, right? First off, you wouldn't have a three-phase power system. You'd only have one single phase. And secondly, this bottom over here actually connects to the top over here, doesn't it? Wouldn't that short everything out? So we don't have them in series. The same thing with the Y. So if you put the ones in series like that and then add them together, that's problematic. You need to just kind of refocus on what is a delta and what is a Y. From a single phase equivalent, all you see is one resistor or one load from each element. You don't see all three connected. You're just looking at it from the equivalent.
Can you convert from delta to Y?
I did both. So if I put them both in Y, I had 2.24 and an angle of 51.7. And delta, I had 6.72. Whoops. Guess I can't. At an angle of 51.7. Only the magnitudes change, but the angle should be the same.
Well, those are your final answers or?
Those were my final answers, putting them in parallel, yeah.
So you convert one delta to Y,
Or the Y to delta, either one would work.
and then since they are both in parallel, you use the parallel to.
Yep, 1 over Z1 plus 1 over Z2, invert that.
It's just the single resistors.
The single resistor, yep. Because again, when I talk about a resistor in a three-phase system, I don't have one resistor. I actually have three resistors. So most of the time in a three-phase system, I call it a resistive load bank or a capacitor bank, because that means it's three capacitors. It's a bank of capacitors. It's not one capacitor, it's three of them. So when I say the resistor in a three-phase circuit, I might be misspeaking, but it should be the resistor bank in a three-phase circuit. Questions on that?
Is that using Z delta equals 3 times CY, is that? the equation?
Yes. Yep, you multiplied it out. And you get it that way. So actually, no, to go from delta to Y, I have to divide by 3. So ZY equals Z delta divided by 3. Any further discussion on number 2? All right, let's move on to number 3. Number 3 was just power factor correction. So some people, and I'm assuming you went on the internet to do this, this is perfectly fine. You just got to be careful when you start using tangents and you start subtracting angles. That works, but if you don't understand what you're doing, you can set yourself up to get into trouble. So what we talked about in this class hopefully kind of makes it yelling at you, which is here is my original power triangle. Here's P original, Q original, and I don't even need S original. I just need P and Q. Then here's my new, this is what I want for my power triangle. So this is P. This is what I want for power, right? But a cap bank can't provide any real power, so I just call it P original. P doesn't change when I stick a cap on there. What does change is my Q value. So that's my Q new. So if I was to draw a line between the original and the new, this is what that capacitor needs to be to knock down that original power factor to the new power factor. So you had two power triangles to draw, the original and the new, and then you just calculated Q. So in the first case, I calculated, let's see, I calculated 9.3. And in the new case, I had to calculate, or I calculated right around 4.9. I can see that Q cap is the difference between the original and new. So let's write the equation. Now, can I immediately run that into my equation for V squared over X sub C? I told you what the voltage is. It is 138 kV, three-phase. So can I immediately go ahead and just plug that in and solve for XC? I have one nodding of no. Anybody else? Well, first, let's draw a picture. What does the cap bank, what do you want the cap bank to look like? Delta or Y? That does make a difference, right? I did delta mainly because my voltage is the highest in a delta, but you could have done a Y. So this three-phase cap bank is responsible for 4.4 megabars. What is each individual capacitor responsible for? Square root of 3. Is Q a phasor? It's just responsible for 1/3, isn't it? So Q for the individual cap, so we'll call this cap bank, we'll just call this cap, has got to be 4.4 divided by 3, which is going to be equal to V squared over X sub C. Which V squared did you use? In a delta, it's a 138. In a Y, so here's my Y, here's 138. This is when I would use the square root of 3. But in a delta, I don't need to. That's why I want the higher voltage. So this is 138 kV squared. Solve for X sub C. Once you got X sub C, solve for C. My value of C was right around 29 mics. So just to reiterate, it's perfectly fine to go on the internet and find different approaches. But what people were trying to do with tangents and all that stuff, they were trying to combine these all in one step when you start doing inverse tans, because that's what you do to solve for Q. You take the inverse tan. But the problem with that is that you start losing sight of what are you really trying to accomplish. I'm trying to make Q lower. When I do my two power triangles here, that screams at me, hey, you're trying to get this Q new down. It yells at me, that's what I'm trying to do. So then you can logically process it. I've had a couple other students calculate X's. So they would calculate X over here and then X over here, which is okay. But keep in mind, the problem description is how do I improve the power factor? It wasn't how do I make the reactance go up or down? Because when you do it in terms of reactance, you start to lose sight again of what you're trying to do. So just do the power triangles. And then hopefully once you get familiar enough with them, it'll actually start to follow and make a lot more sense. Questions on number 3?
Is that 29 your final answer?
Well, it depends, right? Because you could have done delta OY. So it depends on which way you did it. I had 29, roughly.
And that would just be for
One capacitor. But it's a cap bank of 29 microfarad capacitors. So I've got 3 of them.
See, but you don't need to multiply that.
Do I multiply that by 3? I'm going to go to the store. I'm going to go to Home Depot and I'm going to buy a 138 kV, 29.9 farad microfarad capacitor or a 90 microfarad capacitor to build my cap bank. I'm not going to do either of those. I'm going to go to Home Depot and I'm going to say, I want a 138 kV 29 microfarad capacitor, but I don't want a capacitor. I want 3 capacitors. Can't do it with one. It's a single phase load. We talked about this class, everything being balanced. So everything should be the same. If you just put one capacitor across that phase, then the rest of the other 2 lines are going to be very different results. And now a lot of the analysis stuff that we do in this class is going to be null and void. It's not going to work for us. Questions on number 3? Is everybody confused or just very quiet for one reason or another? I don't know if I should keep going or, yes, sir.
You here, that's the, let's see, 1/2.
Oh, yes, 1/2 pi, sorry. Yeah, it's 1/2 pi, sorry. Keep going or pause? All right, number 4. 4 was really just a chance to see if you could do AC circuit analysis. So I have a 2 ohm resistor in series with a 7 millihenry inductor. The circuit is energized by a 120 volt RMS power supply. So here's my power supply, and I'm going to pick this at an angle of 0. First off, it's magnitude and angle, so the voltage should have magnitude and angle. Secondly, 120 is the RMS. Should I multiply that by square root of 2? Yes or no? How come I had a lot of tests that did though? When I multiply by square root of 2, what am I getting? I'm getting a peak value. That's not what we do AC circuit analysis in. That's why I used 120 volt, because when you plug in your outlets, it's a 120 volt outlet. That's RMS, not peak. So you shouldn't have needed the square root of 2. Now we're going to add our resistor and our inductor, 7 millihenry. Now we can calculate the current. Right? No. Because to do AC circuit analysis, we can't go R equals 2 plus L. We need to do R equals 2 plus JXL, which means I need to multiply by omega. So if you want to do circuit analysis here, you darn well better put your J omega term in there and multiply that out. Otherwise, you're not doing AC circuit analysis. Then you'd have to go back and either do time domain analysis, you could do Laplace domain analysis. But in AC circuits, the reason why we multiply that is because if I wanted to solve for the current in an RL circuit, L d I dt is the voltage, right? So I'd have some 167 times the sine of omega t is going to be equal to R times I of t plus L di dt, right? Those are the voltage drops across each of those elements. That's if you want to do it and keep it as an inductor. You can also do everything in the Laplace domain if you want. It doesn't bother me. But this is the base, this is the time domain representation. But I don't want to do that here. I want just the steady state values. So I convert everything with J omega. Now it's all AC circuitous. And now I can say that my voltage here is going to be equal to this, or my current. A lot of people, just be forewarned, I'm a little nervous about some of you people doing calculators and entering it in, because a bunch of people just said I is equal to 120 divided by 2 squared plus XL squared square rooted. This is going to give me the magnitude of Z, but what does current have again? We said at the beginning of class. And magnitude and angle. If I just did this, I've only got the magnitude. And that's not what the current is. The current has more of that. The problem description is, what is the current from the power supply? You should be able to enter it in your calculator pretty easy. I did give everybody the option to use MATLAB too, right? MATLAB, and this is for Avery because she said, how would I enter that in? Do a little tutorial. 120 at an angle of 0 is just 120. Divide by 2 is my resistor, plus J times omega, which is 2, times pi, times omega, which is 60, times 7 milli, you can go 0.007, or you can do E3. That's I. MATLAB is only able to produce, its base is only be able to produce numbers in rectangular coordinates. So I've done this a bunch of times. I've developed, or I showed you how to write this little quick vector. So display I, which is going to display it in polar. So I need the absolute value of I and the angle of I times 180 over pi. I need that 180 over pi because MATLAB only works in radian mode. It doesn't work in degrees. So your final answer, why is this taking so long? There's your answer. Nothing up my sleeve, right? Because you just showed me do the calculations. So this is just the equation you need to do. I know your TI-89s can do it. I don't know, that's an 84.
I haven't.
You can't do complex numbers in 84s like that?
You can't do the angle, it displays it as magnitude e to the like I, and then whatever your angle is.
So what one of your classmates said is that it displays it as e to the I angle.
Believe so. It's been a minute since it.
So then I haven't seen, because I thought it was trying to show it to me like in degrees and radians, so I didn't want to do it. And then, but I've been able to the exam on playing my calculator on but I did not. There was no.
So your calculator, you can't switch between radian and degree mode?
And then I'll switch it to degree and then it'll be like, this value is supposed to be entering that long out up there, but that's what it is.
Yeah, usually calculators can go either one. I'm surprised it can't.
Yeah.
Every time you enter the angle, it's expecting it in radians. So if you enter the angle in degrees, you have to put times pi for 180
Yeah.
after it.
So you just, if that's what your calculator expects, I think the TI-89s you can enter in degrees, but is this wrong? Your TI-89 does the same thing. You just use this. But your TI converts it to that. That's Euler's identity. We talked about that in this case. This is how I would enter it in MATLAB. M times e to the j theta is exactly how you enter complex numbers in polar form in MATLAB. Your TI-89 does it. It just gives you a nicer front end so you can use the angle symbol. So if you do have to do e to the j theta, it's just as easy to do it in MATLAB, so you can take your pick. Question on number 4. Number 4, I was hoping was going to be really quick and straightforward. I was surprised to see a lot of people struggle with it. So, and I don't know if that's because of the AC circuit analysis, particularly doing the magnitude one, where you did Z, where you calculated the magnitude. So what that leads me to believe is that you might have been taught to try to avoid using the complex number calculators and doing it that way. That in this class and the following class is a path to ruin. Not exactly, but you will have a very difficult time if you try to do everything with magnitudes and angles and doing them separately. You've got to learn, just from an efficiency perspective, you've got to learn how to enter numbers in with complex numbers, either your calculator, and like I said, MATLAB can do this all day long. It's a little bit harder to enter the numbers in, but it's the exact same thing. So whatever work you need to do to make sure you're understanding that, it's just complex numbers, TJ.
Oh, the equation you wrote, you did this time I sub t plus angle here, right?
I sub t? You mean right here?
Oh, yeah.
I don't want you to write this equation. Go back to 210 for that equation. We do everything in circuit analysis. So I just want I equals V over Z. This equation is if we were doing everything in the time domain. We don't live in the time domain in AC circuits. Everything is steady state. Okay. All right. Unless there's further questions, let's go to number 5. Number 5, you have a delta connected system. Picture tells 1,000 words. And VAB, VBC. And I gave you each of those voltages. And I said, determine the line voltages. Line voltages are the voltages across these. Isn't that the same as the phase voltages? Or aren't those the same as the phase voltages? So problem A, the answer was what was given to you in the problem. 480 at an angle of 30, at an angle of 270, and at an angle of 150. Those were the line voltages. For B, determine the phase voltages. The phase voltage is across here, right? Isn't that plus the same as that plus? And that minus the same as that minus? So in delta, line voltages and phase voltages are the same. So A and B were the same answer. No difference. And then for part C, all I was looking for was that. I wanted the phasor diagram. Remember, a phasor diagram has 3 vectors that are rotating in that manner. So this is VAB, VBC, and BC. Questions on number 5? Yes, sir.
First C, we not.
You mean put the 120 degrees? You needed the 120 degrees because isn't this the phasor, the phase relationship between those two? Yeah, as long as it looked like it was around 120 degrees, I was fine with that. It just had to be ballpark 120. Okay. Number 6 was transformer open circuit tests and short circuit tests. So build a table. Open circuit, short circuit. Let's see. So I have V, I, and P, right? Those are the only 3 things that I need for each test. So for V open circuit, I have 2400. I open circuit, 0.208. I'll just put 0.21. And P, 185. And for the short circuit test, I have 615. I have 20.8. Sorry, I'm not putting these in order. I'm just putting them down as I come across them. And then V is 52. So if you want to keep it on the table, do my power triangle. So I'm going to calculate this. This is where I'm doing my calculations. So this is not P total, this is power triangle. I have 185. I have 0.21 times 2400. Over here, I have 615. I have 20.8 times 52. Now I can calculate theta open circuit and theta short circuit. So continuing up, I've got my theta. So theta open circuit is equal to the inverse cosine of 185 over 0.21 times 2400. And I'm writing these just so that you know they're different. Cosine minus 1, 615, all over 20.8. This is really touchy, sorry. Times 52. Once I have that, now I can build my I. So I is going to be equal to 0.21 and an angle of minus theta open circuit. I is going to be equal to 20.8 at an angle of minus theta short circuit. And now this is where I'm probably going to stop using the table because the way to calculate them vary a little bit. So I'm going to calculate Y open circuit as my open circuit current divided by my open circuit voltage. And over here, I want Z short circuit is going to be equal to my short circuit voltage divided by my short circuit. Oops, I said that and then I wrote. It's my I short circuit. Don't forget this has an angle of 0. This has an angle of 0. I've already defined those. And this one here is equal to R equivalent plus JX equivalent. And this one here is equal to 1 over R sub C minus 1 over J X sub M. Wasn't anything tricky or confusing. This was just like we did in class, just like the homework, no deviations. I got 31.1K, 12.4K. R equivalent was or is 1.4, and X equivalent is 2.1. That was it. Now I tried to make this easy because I put both tests on the same side of the transformer. I think if you looked at the data, everything was on the primary side of the transformer, so you didn't have to reflect any impedances one side or the other. They were both on the same side. So hopefully that made it a little bit easier. Question on number 6. Yes, sir. Yes, that's one of the things I talked about this class. Voltage is almost always at 0 because it's easy to measure and it's good to do a reference. We may change that on occasion, but for the most part, voltage is at an angle of 0. And it's important that you do that because if it's not at an angle of 0, remember theta on your power triangle is the same angle between voltage and current. So if you pick an angle of 0, you can just copy that angle and then just put it on your current. If you pick it at 10, then you have to add or subtract your thing from 10, and it just makes it more complicated. So pick it at 0, and then that's the same angle. Yes, sir.
Question about 50K EA that was that. You don't use that at all.
You do use it. The 50 kVA was when you calculate the short circuit current.
Okay.
That's what the current you would do. But did you need it for any of these calculations? No, that's just to actually do the test. Just like if anybody did the transformer, the bonus for the exam, it's the same thing there. We needed to know what the impedances were. So we needed the 68 MVA or the 80 MVA, whatever you use, we needed those data points. So you need it for the baseline data, but it actually isn't part of the test. Last problem. So I have a 1200 to 5. So remember my CT. The primary winding has one turn. The secondary winding has all the other turns. So this is 1200 to 5. So I take 1200 amps and I convert it to 5 amps, right? Which means the current goes down, so the voltage has to go up. So the turns ratio here is going to be 1 to essentially 240, right? 5 times 240 is that. So then I said, all right, well, I know what the turns ratio is. The drop across the load is 50 volts. VP over VS is equal to 1 over 240. Yes, sir? The CT is rated for 1200 to 5. if the primary winding has one turn, how many secondary turns is it gonna have to set the current down by a factor of 5?
Oh. Yeah, okay.
And actually, it's not 1 over, it's the other way, sorry. 240 to 1. So VP equals 241, or do I have it backwards? Let me think for a second. If the current is going down, no, it's 1 over 240. Has to be 1 over 240 because if the current is going to go from 1200 to 5, the voltage has to increase on the secondary, right? So the voltage has to increase on the secondary for the current to decrease. They're the opposite of each other. So VP is equal to VS divided by 240, which I had as about 0.2 volts. And that's important to us because we don't want big voltage drops in our system, right? So 0.2 volt drop across that CT is not that big of a deal. Now, this next part, what is the power from the trend? What is the power that is drawn from it? A lot of you people said, oh, it's 50 volts squared divided by 1, V squared over R, right? But what did I say? What's one very important thing about transformers? They saturate. They are non-linear. So if this transformer is operating, it's probably someplace over here. You're getting more current out, and it's working extra hard to drive that voltage. If I redraw that resistor, what's the voltage here? What's the current? What's that?
It's given that that resistor is 1 ohm. So how do you have 5 amps? Given 50 volts?
Because what you're assuming is the power supply is doing this. The power supply is non-linear. It is at 50 volts, but it can't drive that whatever current that would be for 50 amps, for 50 volts. It is over here. It is oversaturated. You're trying to pull too much power. So the power supply, this is the power supply. This R does not equal 0. You're dropping some voltage across it. That's not knocking down your current. So that's the reason why. It's a non-linear device. So it's not 50 divided by 1 because that would assume a linear power supply. This thing can't drive 50 amps at that voltage. If you tried to drive 50 amps through it, what would happen is the transformer would be it would be someplace down here. Its voltage output would just crash because you're trying to overdrive it. Yes, sir.
I got these, the primary and the primary voltage, now we got 250, are they supposed to be controlled?
They should be, yeah. Yep.
Yeah, just so there's no.
No losses in the CT. We're assuming there's no losses. Think about it.
Still struggling with
It's not a linear power supply, it's a non-linear power supply. So your voltage is changing. You think you get 50, but once you try to drive more current, the voltage drops. Right? If you try to drive more current, your voltage drop across here increases. And so it's like an equilibrium state.
It's specified as the voltage cross, the voltage drop across the load is 50.
So you put 50 there, but the current coming out of this, right, is limiting. So it's almost like a dependent power source. If you try to go above 1 amp or 5 amps, then the voltage drops. So it's not a linear device. It's saturated. If anybody, let's see, do I have curves? If you look at a CT saturation characteristic, Let's see if I can find a curve. If, here. So as you start driving it, it's linear. And then once you get here, you're really trying to push that hard. So now the voltage just drops. But if it was perfectly linear, it would just continue to increase the current. But it peels off. So that's the problem. It'll bend your brain because you've always assumed a linear power system, a linear power supply. These are not linear. They saturate. And that's the test. You feeling better or worse after our discussion? What's that? Frustrated with me? Was it confusing how I asked stuff, or because I had a couple students say, I just really need to read the problem.
It's a lot of three-phase stuff. And it really tracks a lot of three-phase, only stuff for the single phase, so it's going on.
Well, I would say that, let's see, problem 4 was single phase. Problem 5 and 6 were single phase, so almost half the test was single phase. The other half was 3-phase. But this whole semester, it's important for us to do 3-phase because transformers are 3-phase, motors are 3-phase, generators are 3-phase. It's pretty, we do everything from a single phase equivalent. That's the nice thing is we can convert a 3-phase system to a single phase equivalent just by using some of the stuff we've learned. Any other? Yes, sir. What was confusing about how I explained it here? Even if you didn't get the power, my hope was that you could have got this part of the problem pretty easily, because it's the turns ratio, right?
I would say one thing that about the ratio is because it's actually 1/41, or I mean 1/29, it's 1/1. That kind of like what I was like, if it's 1 on this side, it must be 1, we're like, that's just must be really high than that.
Well, here's our turns ratio. It's defined as VP over VS. And for transformers to be constant power devices, and we derive this, they have to be the inverse of each other. And that's what I always tell people, like, oh, and even I put a 1/240, then I changed it to 240. It's like, no, it's not right. You have to think about it. I'm stepping the current down from primary to secondary. And if I want that transformer not to get power to lose power, the voltage has to go up. Right? So stepping down means you're stepping the voltage up. That's why the turns ratio is opposite. So I would say, you know, if you didn't do as well as you wanted to, I mean, don't panic. Just because it's, for many, this is the first time taking a test with me. And I know John, if you've taken 312 with him, you know, we have different expectations in terms of what's going on. And that's not a put down of John. It's just, we just, you know, in this class, because we have to do everything with magnitude and angle, we can't do shortcuts with you know, because the whole time you're going to be sitting there doing these calculations. It's going to drive you nuts. You're going to do those thousands of times. Just get comfortable with your calculator entering it in. Your calculator should be able to handle it. If not, MATLAB can definitely handle that. And then just get comfortable with it, and then you can work from there. If you really didn't understand like problem 4, so, you know, 4 might have been a little bit different, but that hopefully was just a review question from AC circuits. It was just simple RL series circuit that we analyzed in the steady state or AC domain. If that one is no clue, then, you know, maybe we should have a conversation about that. The power triangle stuff, I wouldn't get too worried about. As long as you see it in the, you know, with the exam, we'll get a lot of practice because we do power triangles a lot in this class. And if you follow on with this class, we do it all the time. But for the most part, we won't have to worry, you know, too much. I wouldn't get too worried about it because it's not a really complex topic. You just have to remember how to do it. Any other thoughts, comments, questions? Do you have enough time? Did you like, even though it was 8 AM, I know. Did you feel like time was sufficient? Some of you got me yelled at by Jude because you missed project management. And I said, you know, they had an option to take it on Friday. So. Oh, so she was giving me a hard time for a class that she canceled. Wait till I talk to her. No, it's fine. But the thing I want to stress is that, you know, nobody here is more important than anybody else. We're all equal. So if you have to miss a class, you know, check with the teacher first. I would never give you authorization to skip a class. I would just say, you know, let's make an accommodation some other way. If that other instructor is satisfactory with you doing that, then that's a different discussion. But you should always request permission first. And if not, then we'll figure something out.
I just didn't think it was gonna take more than 2 hours.
Yeah, because I mentioned that to you. I was surprised. I didn't expect most people to take that long either. So I was hoping most people would have been out of there in an hour and a half.
I like the longer time. I caught a few of my errors. Rewriting is a problem. I worked in a mess, so I had like problem 1 on the back. I got one and problem 7 on the back. So I cropped it out and rewrote it. So I like the extra time. That was kind of not worried about the dropping that focus on.
Yeah. And I agree, because that's what I would do with a test. I would have all the scratch paper and I would write it all out. And then I would go back and then I would copy it over to see if all the math made sense and all that stuff. So as long as you have enough time, it really does put you at ease.
I did the 3 first problems completely wrong, went back and redid them, so.
That ate your time.
That took me. Yeah.
Well, the question is, why did you think you did them wrong in the first place? That's the question. Is what happened? Why did I think that? And then go back.
Later on, like one of the other questions, the way I've read it, it got me thinking about phase versus line, and I realized that I had the wrong voltages and whatnot. It's some funky stuff. So.
Yeah. Draw a picture. If you're stuck, look at phase and look at line and a delta or y, and then it starts to get obvious for you. Yes, ma'am.
The first time they looked at it, look over maybe after following, there was something, you know, that, like, if we have like plenty of marketing.
Okay, good. I guess I asked that question is because there were a lot of long faces at 8 AM that morning. Everybody walked in like, do we need to be here? I'm happy to do it during class at 11, but I can't give you more than an hour and 15 minutes. That just doesn't work. So I know it's early and I feel bad for that, but that's Office of Student Records, I think, sets the schedule. I have very little control over that. So, and the only other option would be to pick a time where everybody could make it. And if I have a volunteer to pick a time when everybody in this class can make it, a 3-hour block, then you can get an A for the semester, because I've never done this for 20 years. I've never once been able to do that.
I feel like 1 to 4.
I did that.
1 to 4 AM? You'd rather do it 1 to 4 AM?
Schedule's probably over.
You would be shocked. You can try, but with 30 students in the class, it's just not going to happen. Even with lab, we can't. We have a dedicated lab for most of the class, and we can't do it.
Nah, until after.
So it just doesn't work. Even if we did 5 to 8, people have to work. People have lives. Does anybody want to be taking a test 1 to 4 AM? Yes?
You legitimately have to be like 10 to 1.
Yeah. But even then, people will be falling asleep. I mean, how productive are you at 10 o'clock? I would not be productive. Something to think about. All right, any other questions?
Do this thing.
All right, if there's nothing else, have a great day. And I will see you all on Thursday. Take care, everyone.